Hello, you're welcome to the chemistry series with Excellent Simplified, and today we are going to be looking at elements. Now, an element is any substance that cannot be split, that cannot be broken into simpler units by ordinary chemical processes. I take that again. An element is any substance that cannot be broken down, that cannot be split into simpler units by ordinary chemical processes or reactions. So take for example, if this is an element, what that simply means is that I cannot split this element into simpler units. Do you understand? So an element cannot be split into simpler units by ordinary chemical processes. Now, that's an element. Now, in the periodic table, we have about 118 elements. So we have 118 elements. And out of the 118 elements, 94 of them occurs naturally. 94 of them occurs naturally, while the remaining 24 are artificially made. Do you understand? 94 occurs naturally, the other 24 are artificially made. Now that we've known the meaning of an element as any substance that cannot be split or broken down into simpler units by ordinary chemical reaction, now there are three classes of elements. We have two main classes and one extra. Now the classes of elements are metals, non-metals, and we have a third one, metalloids. But I'm going to take the metals and non-metals first, then we talk about the non-metals. Now, metals and non-metals. Let's look at them side by side. First thing here, metals are elements with characteristic metallic luster that reflect light. This luster means they can shine, shininess, they can reflect light and shine. They reflect light, they shine. So metals are elements that can reflect light, can shine. Example, iron. Iron is a metal. Non-metals are elements with no metallic luster, hence do not reflect light, except diamond. Now, non-metals cannot reflect light, so they are not shiny. Non-metals are not shiny. Metals are shiny. Now, number two, metals are good conductors of heat and electricity. So, metals are elements that are good conductors of heat. They can conduct heat very well, and they can also conduct electricity. Non-metals, on the other hand, are poor conductors of heat and electricity. I seen it now. They are poor conductors of heat and electricity. Now, number three, metals, some are malleable. Some are malleable. What does it mean to be malleable? It can be hammered into thin sheets. You can hammer metal into thin sheets. You can hammer it into thin sheets. But non-metals, they are brittle. You cannot hammer them into thin sheets. They are brittle. They can easily flake. But metals are malleable. You can hammer them into thin sheets. Now, some metals are ductile. And that means it can be drawn into wire, can be drawn into thin wire. That's that. But since non-metals are brittle, they can break easily, they cannot be drawn into wire. So they are not ductile. The fifth one here, metals have high densities, except magnesium and aluminum. They have very high density. Now, non-metals, they have low densities, except iodine. All right, so high density, low density. Now, the last one here is metals have high melting and boiling points. High melting and boiling points, except mercury. Mercury is a dense liquid actually, but metals generally have high melting and boiling points. Non-metal, on the other hand, have relatively low melting and boiling points. So these are some of the characteristics of metals and non-metals. Now I mentioned the third one, metalloids. Metalloids, they have a characteristic that is intermediate between metals and non-metals. So metalloids are in between metals and non-metals. They can have some properties of metals and some properties of non-metals. Examples of metalloids, we have silicon, we have germanium, we have boron. They are metalloids. They are metalloids. All right, so that's that about the classes of elements. Now, In 1818, Jones Berzelius came up with something. He said, why not give symbols to these elements? Remember I said we have 118 in the periodic table. Now, why not give symbols to represent these elements instead of writing them always? I said, who did that? Jones Berzelius. See the spelling of his name here. Jones Berzelius. He actually did that in 1818. He gave chemical symbols. Chemical symbols are letters used to represent elements. Now, one thing you need to know about these chemical symbols is some of them, they are just one letters, and the one letter can be the starting of their name. Some they use two letters, the first letter of their name and any other letter. Some of them they use letters from maybe their Latin name. We'll see that as we go on. But in any ways, if you have two letters to represent an element, the first one is always capital letter and the second one is always small letter. Now let's look at the first 20 elements. I will use that to show you the atomic number. As the video goes on, I will explain what atomic number is, but for now, just look at this. This is the number it appears. Now, the atomic number, the elements and their symbols. So I'm using the first 20 elements. Then I'll give you the acronym to use and remember that. Please, the first 20 elements is a basic in chemistry. So you'll be using it in all the topics basically all the topics in chemistry, that knowledge. So you have to know it offhand or offhand. How did they put it? You have to know it anyways. So you have to know them, the atomic number, the element and their symbol. Know it in your hand, your fingertips, because you use it in all the topics you're going to be treating in chemistry. All right. Now that being said, the first element here is hydrogen, and as you can see, the symbol is H, capital letter. Helium, He. If you notice here, the H is capital and the E is small. So the next one is lithium, Li, beryllium, Be, boron, B, carbon, C, nitrogen, N, oxygen, O, fluorine, F, neon, Ne. The N is capital, the E is small. Please, at this point, if you are not used to the first 20 element, pause the video and write them down, write them out, and ensure you get it right. You use this acronym also. Now, sodium, Na, magnesium, Mg, aluminium, Al, silicon, Si, phosphorus, P, sulfur, S, chlorine, Cl, the C is capital, the L is small, argon, Ar, potassium, K, calcium, Ca. Now, this is the first 20 elements on the periodic table. Verse 20 elements on the periodic table. So remember this, you can always use this acronym. There are many acronyms. In fact, I know 2 songs you can use to remember this. Remember this song they used to sing. Jingle bell, mosquito now. That song. You can actually use that song to remember that. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. So you can actually use that. Or you use this acronym. He has little brain but cannot offer full 9 subjects. May all silly people stop calling all Pope Christ. Where he, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So you can actually use this acronym to remember this. Please, if you're learning this for the first time, calm down, pause the video, write them out and memorize them, because you use this principle throughout in chemistry. So far we've looked at the meaning of elements, we've looked at metals and non-metals, and we've looked at metalloids also, that's the classes, and we've said that there are 118 elements in the periodic table, out of which 94 are naturally occurring, while the other 24 are synthetic. That's all we've said so far. And we've looked at the first 20 elements, the atomic number, the symbol. All right, so that's basically what we've done so far. Now, the next thing is we're going to look at compounds and mixture. Compounds and mixtures. All right, so we've looked at elements in details. Now let's look at compounds and mixtures. Now, starting from compound. A compound is any substance that contains two or more elements combined together in a fixed or definite proportion. So, a compound contains two or more elements chemically combined in a fixed proportion by mass. While a mixture is any substance made up of two or more compounds that are not in definite proportion. So in mixtures are physically combined. The constituents are physically combined and they can be combined in any proportion by mass. What does that mean? A compound contains two or more elements chemically combined and they are combined in definite proportion by mass, while a mixture contains two or more compounds or substances physically combined in any proportion. Now let's look at that in details. These are compounds. These are the compound elements, that is the constituent elements, the elements that make up the compound, and this is the formula. Now, water is a compound. Water is not an element because water contains two elements combined. Remember, a compound has two or more elements combined. Now, water has hydrogen and oxygen chemically combined. Remember, we said compounds, the elements are combined in a fixed ratio, definite proportion. Now, in this case, we have two molecules of hydrogen and one of oxygen. So you can see there is a definite ratio here. So water is always two molecules of hydrogen and one of oxygen. So the ratio here is 2:1. The ratio of hydrogen to oxygen here is 2:1. As you can see,
is sand, and sand is actually a compound. Now there's a difference between sand and soil. Soil is actually a mixture, but sand, the one we're looking at here, is a compound. And sand is made up of silicon and oxygen. Those are the two elements, silicon and oxygen. Now, Si is for silicon, O is for oxygen. If you check the ratio, remember we said compounds exist in definite ratios. 1:2. One molecule of silicon and that of oxygen, 2. Alright, now limestone is the next compound here, and the compounds that make up limestone are calcium, carbon, and oxygen. So you can see it here, calcium trioxocarbonate. I will teach you how to name compounds, but for now that's it, calcium trioxocarbonate. Now, common salts contains sodium and chlorine, sodium chloride. Ethanol contains carbon, hydrogen, and oxygen, and this is the chemical formula. So these are some examples of compounds with their component elements and their formula. Now, I've told you that compounds, the elements are in definite ratio, while mixture contains substances or compounds that are not in definite proportion. Now we're going to look at the difference between mixture and compound. But before then, water is a compound, right? Good. What if I have blood? Is blood a compound? First thing you should ask yourself before you answer that question is, are they in definite proportion? The constituents of blood, are they in definite proportion? Another thing you should also ask yourself is, the components of that blood, are they chemically combined or they can easily be separated from each other? So if you can easily separate them, then you know it's a mixture. So blood is actually a mixture. Now, the difference between mixtures and compounds. Number one, it may be homogeneous or heterogeneous. Alright, so we can understand this better. Let me talk about the two classes of mixtures. The two classes of mixtures are homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures and heterogeneous mixtures. When we say homo, same kind, right? Now, homogeneous mixture, the constituents of that mixture, the components of that mixture are in the same phase. What do I mean? They are in the same phase. Either they are all gaseous, all liquid, or all solid. The constituents of that mixture, they are in the same phase. While heterogeneous mixture, the constituents are not always in the same phase. Now, homogeneous mixtures form solutions. solutions. For example, if you have salt and water, salt is solid. But if you put the salt in water, what will happen is the salt will dissolve in the water, making it a liquid phase. Do you understand? So that's homogeneous mixture. But in heterogeneous mixture, you can have solid, liquid combined together. Take for example, you take something that does not dissolve in water, say stone, put it in water. What you're having there is heterogeneous mixture because they're in different phases. Do you understand now? So those are the two classes of mixtures. Now, mixtures can either be homogeneous or heterogeneous. But compounds are always homogeneous. Compounds, the components are always in the same phase. Now, the second one, constituents are easily separated by physical method. You can easily separate mixtures, the components of mixtures. Take for example, the blood I use. If you take your blood sample and put it in a test tube and allow it to stand, you discover that the blood cells will settle down and the plasma, the liquid part, will be separated, will be up. Is it not? Stone and water, you can easily separate them. So mixtures, the constituents of mixtures can easily be separated. But for compounds, the component elements are not separated by physical means. If I give you water, water we say is hydrogen and oxygen, H2O. If I give you a cup of water, can you look at the cup of water and separate the hydrogen from the oxygen? Or have you ever fetched water before and you see hydrogen floating one side, oxygen floating one side, and you can easily separate them, except you're a magician. So that cannot be possible. So the components of the component elements of a compound are not separated by physical means. Another difference between mixtures and compounds: mixtures cannot be represented by a chemical formula. What is the formula of blood? There is no formula because it's a mixture. Do you understand? So mixtures cannot be represented by a chemical formula. What is the formula of soil? There is no formula. But compounds are easily represented by chemical formulas like sand. Sand is a silicon dioxide. Common salt, sodium chloride. Water, H2O. They have the chemical formula, but mixtures do not have chemical formulas. The next one, the properties of mixtures are the sum of the individual constituents. So if I have a mixture, the property of the whole mixture is a summation of the individual constituents. For example, if I have a homogeneous mixture like a salt solution, that is if I dissolve salt in water, you discover that the property of that mixture is the summation of the property of water and the property of the salt. So if I give you salt in water and sugar in water, you actually know this one is salt solution, this one is sugar solution, because the individual properties of the components is what determine the overall property. But the properties of a compound differ entirely from those of its component element. Take for example, water, H2O, hydrogen and oxygen are the constituent elements. The property of hydrogen is totally different from the property of water. The property of oxygen is totally different from the property of water. But when you combine both together, it will give you something different, water. So the properties of a compound differ entirely from those of its component elements. So these are some of the differences between compounds and mixture. So far, we've looked at the definition of elements, we've looked at the definition of compounds, we've looked at the definition of mixtures. We've looked at the two classes of mixtures, homogeneous mixtures and heterogeneous mixtures. We've looked at the differences between mixtures and compounds. Just as this series is, at the end of every series, every video, there's always a past question at the end. So there will be a past question at the end of this. So let's move on to the past question. The next thing I'm going to be treating in the series, you still see it there. But first, let's move on to the past question. If you've not subscribed to this channel, please click on the subscribe button so you don't miss out on any topic in this series. Remember, I said we are starting from the beginning of chemistry to the end. Click on that subscribe button and then move on to the past question. Let's go.